You know, in the previous video, we have seen grouping dielectric material and its equations and problems. In this video, we'll see electromagnetic waves in good conductor. Okay, so for good conductors, we know that the sigma by omega epsilon ratio should always be much higher compared to 1, right? And if this is the case, then the propagation constant equation will be given by this formula. We have used this formula in the previous two problems also, right? So whenever we have sigma by omega epsilon or sigma itself is very much greater than 1, then we'll have to use this formula for propagation constant calculation, right? So here it is root of j omega mu into sigma plus j omega epsilon. And if this ratio sigma by omega epsilon is very much greater than 1, can I say that sigma is greater than omega epsilon can be taken to the side. So compared to omega epsilon, the sigma value is very high. So I can just ignore this, right? It becomes very insignificant. So in this equation, I can ignore this term in which then this results in a formula like this, right? So in the previous problem, with this assumption that our sigma value is very high compared to omega epsilon, I can remove this insignificant term, in which case I will be getting the equation for propagation constant as root of j omega mu sigma. Okay. In this further, what they have done is they've kept this omega mu sigma as it is. They've taken this root j. If I convert this, see, j1j, this is nothing but rectangular form. If I convert it to polar, it becomes 1 at an angle 90 degree. Okay. So root of angle 90 degree will be 45 degree. Okay. And this can also be written like this, e power j theta or e power j 45 degree, which is nothing but sine cos theta plus j sine theta. It is cos 45 plus j sine 45. That is what is done. The angle is converted into this format. Cos 45 plus j sine 45. Okay. And then this cos 45 is 1 by root 2. Sine 45 is also 1 by root 2. So that is how we got this equation. And next what they have done in this is omega is replaced by 2 pi f. And if I open bracket and multiply this becomes square root of 2 pi f mu sigma divided by root 2. So root 2 gets cancelled. What is left is root of pi f mu sigma. Similarly, if I multiply this term with the second one, I'll still get the same thing but with j. So this is root of pi f mu sigma plus j into root of pi f mu sigma. Both the terms are same. So gamma is alpha plus j beta. And here I'm getting this term. By comparing these two, I know that alpha value and beta value are so and so. So both are going to be the same answers. That is alpha and beta both will be equal to square root of pi f mu sigma. So this is the derivation you have for attenuation and phase constant for a good conductor. So remember this formula for good conductor, alpha and beta both are equal to root of pi f mu sigma. Okay. The next one is eta. Impedance is calculated as root of j omega mu by sigma plus j omega epsilon. Again, same concept is applied. This is very much greater than omega epsilon, so this part is neglected. Only sigma is written. And again, if I take j out, root of j is root of 90 degree or 45 degree, and that 45 degree is written as cos 45 plus j sin 45. And cos 45 j sin 45 is again 1 by root 2 plus j 1 by root 2. And by open bracketing and multiplying these terms, we will end up with this equation. Okay, this is going to be the equation for eta, finding out eta, right? So these are the formulas you have to remember for alpha, beta, and eta formulas. Okay, the next thing what they've mentioned here is generally if I have electric wave which is traveling in x direction, I can say it is equal to magnitude, can be a plus magnitude minus magnitude. I'm taking plus magnitude. And the overall wave is traveling in z direction. You might have seen this portion in the derivation, first derivation. Okay. But now if it is a good conductor, when the conductivity improves, the attenuation also starts increasing. Okay. So along with this term, an additional term gets multiplied to this, and that is your attenuation value. Okay, this e power minus alpha z is the attenuation factor. It gets added to your signal. Okay, and overall this completely now becomes the amplitude of the signal. Total amplitude of the signal is actual maximum amplitude multiplied by the attenuation factor. Okay, so as and when we keep on traveling in z direction, as the distance increases, the attenuation also increases, and your magnitude of the wave starts decreasing. Okay, that's what you see here. Initially, when I begin, the amplitude is very high, maximum. But as and when you keep on going, the distance increases, the amplitude starts reducing, and at some time, your signal will be completely diminished. Okay, it will completely vanish because of the attenuation. So, I can say that the total amplitude of my signal is Em into e power alpha z minus alpha z, or Em into e power minus alpha d. Z is the direction in which the wave is propagating. So I can say Z is the distance by which it is traveling, or I can simply write it as D for distance. Okay, and then what they've done here is for different values of D, they're trying to tell me what is going to be the amplitude. When D is 0, if I put D as 0 in this, e power 0 is 1, so I will get the amplitude as maximum value. So when the distance is 0, just the beginning, the amplitude will be maximum. Now when the distance increases, if I put z is equal to d, the attenuation will be alpha at minus alpha d into En. So the sum value has reduced. Now if I make d as 1 by alpha, e power minus alpha into 1 by alpha, this gets cancelled, e power minus 1. E power minus 1 is nothing but 0.37. Okay. And if I multiply this by 100, I'll get 37%. So what I'm trying to say here is when the distance becomes equal to 1 by alpha, the amplitude of the signal is reducing by how much? 37%. That is 0.368, 36.8, or approximately 37%. The amplitude of the wave is decreasing to approximately 37% of its maximum value. Initially, it was maximum Em, right? And after some time, at a certain distance, which is 1 by alpha, the amplitude became equal to it reduces by 37% of its maximum value. Okay, so this distance that is 1 by alpha, by which the amplitude reduces to 37% of its maximum value, is called as skin depth. Okay, this is very important. Skin depth or depth of penetration is nothing but the distance traveled by the wave, the distance through which the wave is traveling, and when the amplitude of that wave is reducing by 37%. Okay, the distance at which the amplitude of the wave is reducing by 37% of its maximum value is called as skin depth or depth of penetration. So as you can see, initially it was equal to Em, then it starts reducing, and at certain point, that is at a distance of 1 by alpha, the value reduces to 37%. This distance, which is 1 by alpha, is called as skin depth and denoted by a delta. Okay, this is the symbol used here. Okay, this is called skin depth. And the formula skin depth is calculated as 1 by alpha or 1 by beta, which is nothing but 1 by root of pi f mu into sigma. This is a formula used for finding skin depth or depth of penetration, where the amplitude reduces to 37% of its maximum value. So you need to remember this formula for skin depth. This is very much required for in problems. Okay. And then these equations you can just go through once. So we'll now start with some simple problems on this. The first question, the amplitude of E just inside a liquid is given as 10 volt. Okay, this is the maximum amplitude of the liquid. Now for a liquid, constants are given, mu r and epsilon r and sigma is given. They are asking to determine the amplitude of the E at different distances, at a distance of 10 centimeter inside the medium for a frequency of 5 megahertz, 50 megahertz and 500 megahertz. So you need to know that the total amplitude of the signal is going to be maximum amplitude into attenuation factor. Maximum amplitude is given as 10 volt. Okay. And now we have to find what will be the attenuation factor alpha. Okay. Distance is also given 10 centimeter. That is 10 into 10 power minus 2 meters. Distance is given in the question. But to substitute and to find out, you need to find out alpha value. So to find alpha value, you have to first find gamma, that is propagation constant, which is given by this formula. All these data are mentioned in the question. For three different cases, you have to do. First, I will take the frequency as 5 megahertz. I'll simplify this. I'll find out the gamma equation. Once I get the gamma value, compare it with the standard formula, alpha plus j beta. So alpha here is nothing but 3.123. So once I get this alpha, I'll put it in this equation, Pm e power minus alpha d, and I will get the actual amplitude. Same procedure is repeated with the frequency of 50 megahertz. In the same equation, omega is equal to 2 pi f, right? So f is changed to 50 mega and you're calculating it again. And in the third case, you're going to use f as for 500 mega and you're going to do the same thing. So one formula and you have to keep on repeating for different frequencies. Okay, so pause the video and you can check how it is done. You can simplify it yourself and see if you're getting the same answers. Okay, so this is how you find out the actual amplitude at different different frequencies at a certain distance. Okay, next question. Calculate eta, gamma, and velocity v for a conducting medium in which sigma value is given, mu r, epsilon r, and frequency are given. So eta, gamma, and velocity equations you know for a good conductor. So for a good conductor, this is going to be the equation for eta. This is the equation for gamma, and velocity is just omega by beta. Okay, so equations, if you know the equations, it is direct substitution. Okay, for a very good conductor, you see this value is very high compared to 1. So sigma plus j omega epsilon is there. No, this term can be ignored and only sigma can be written. That's why you have only sigma here. Actual formula is sigma plus j omega epsilon will be there in the denominator. But since sigma is very high in this problem, they have ignored this term. Same thing they have done here also. The actual formula is this. Again, sigma is very high, so this term is ignored and you're getting this equation. Even if you substitute this and simplify, you're still going to get us answer which is very close to this value. You will not see much difference. Only decimal difference will be there, but you will be getting a very close answer to this. Okay, so this is a formula. Just substitute, simplify it, and find out the result. Okay. Next one. Determine the depth of penetration for copper at 1 megahertz. So one more thing, this is very important. Here directly they have given copper, but they have not given a formula for skin depth is 1 by root of pi f mu sigma. F is given. Mu can be calculated, mu naught into mu r. Sigma you need to know, right? But here they have not mentioned it. So please remember these values. For copper, the mu r value is 1 and sigma is 5.8 into 10 power 7. Okay, you need to remember this extra along with mu epsilon naught and mu naught. You have to also remember sigma for copper. Okay, so once you know this, it's direct substitution, find out the delta. Okay, next, a metal sheet of aluminium has conductivity so and so. Calculate the skin depth delta, propagation constant gamma, and velocity of propagation v at a frequency of 1.6 megahertz. So delta is nothing but equal to 1 by alpha or 1 by root of pi f mu into sigma. You can use any of the formula to find out because sigma is given, frequency is given, mu naught, mu r is also given. Directly you can substitute in this formula and find out the answer. Okay. And second thing they're asking is gamma. So gamma again use this formula. You see 38.2 is very high compared to 1. So you can directly take this formula and substitute. And velocity is going to be omega by beta. Okay. Next one. The skin depth in certain conducting medium is given. Delta is already given and frequency is also given. They're asking to find sigma value. So same formula, whatever is given, substitute that and find out the unknown parameter. Rearrange it and find out. Okay, because you're supposed to find sigma here. Square on both the sides so that you can remove the square in square root. Then rearrange it, you will get the sigma value. And the unit is very important. It is mho per meter. Next, this is also direct formula. Frequency is given, sigma is given, epsilon r, epsilon, mu r, everything is given. And they are now asking you to calculate the skin depth and also depth at which the wave amplitude decreases to 13.5% of its initial value. See, first part is very easy. Skin depth, direct equation, all the values are given, substitute, calculate. The second part, what they're saying is, they're asking you to find the distance or the depth. The depth at which the amplitude is reducing by 13.5%. Okay, so you know the formula for amplitude. Amplitude, its initial value. So if I have EM is equal to so and so, and after a certain distance, it is reducing by how much? This value is nothing but reducing by an attenuation factor, and it is reduced to how much? 13.5% of its maximum value. Okay, this is the actual value multiplied by attenuation factor. So by when at a certain distance d, the overall value of the amplitude is reduced to 13.5% of its maximum value. Okay, so I need to find out what is the depth at which this is happening. For that, I need to know alpha value. Right. So you know the relation delta is nothing but 1 by alpha. So alpha will be 1 over delta. You have calculated delta here. Take the reciprocal of that. That will give you the alpha value. Okay, substitute that alpha here. Right. And then, so what I have now is EM e power minus alpha d is equal to EM into 13.5%. If I convert, it becomes 0.135. Okay, so EM gets cancelled on both the sides. I have e power minus alpha d is equal to 0.135. Alpha you can calculate as 1 by delta. You'll get some value there. So you have now, you take natural log on both the sides. I'll get minus alpha d is equal to natural log of 0.135. So distance or depth will be natural log of 0.135 by minus alpha. So by substitution and simplification, you will get the distance or the depth to be so and so. Okay, here, see what they've done is they've used beta z, but you please follow this only. Instead of e power beta z, you write it as e power minus alpha into d. Attenuation factor as e power minus alpha into d. And continue it, because this is what you learned right now. You know that this is the factor which gets multiplied with the actual voltage, and that is one which is reducing the voltage here, or the amplitude. Okay. Next question is straightforward. Again, I told you copper is given, so please know the conductivity of the copper. If it is not given in the question, you should remember the value. Okay, so direct substitution and finding out the skin depth. The last problem, they've given a wet marshy soil is characterized by the values of the soil are given here. Four different frequencies are mentioned, and they're asking you when the soil is going to behave as conductor and when it is going to behave as dielectric. For different frequencies, you have to tell the property of the soil, whether it is a conductor or a dielectric. So for that, what you should do is to decide whether it is conductor or dielectric, the value you are going to find out is sigma by omega epsilon, this ratio. This ratio, if it is very much greater than 1, it is conductor. If it is very less than 1, it is dielectric. Okay. So for first frequency 60 Hertz, you calculate the sigma by omega epsilon. What is the answer you get? It is, you can see it is 10 power 5 plus 5. So it's very high compared to 1. So it is a good conductor. Next frequency 1 megahertz. You're still getting 11.98, which is greater than 1. So it is still a conductor. Third frequency is 100 megahertz. So if I take the ratio, I'm finding this 0.1198. Not very less than 1, but very closer to 1. So I can say it is a lossy dielectric, not a perfect dielectric. And the last frequency 10 gigahertz, I'm getting a ratio which is very smaller compared to 1. In this case, you can say it is a perfect dielectric. So such questions can be asked in the exam, where they'll give you all the data, and for different frequencies and ask you what is the behavior of the material, whether it is a conductor or a dielectric. Okay, to decide whether it is conductor or dielectric, you need to use the ratio sigma by omega epsilon. If it is very much greater than 1 conductor, if it is very less than 1, it is dielectric. If it is slightly less than 1, it is a lossy dielectric. Okay, so with this, the conductor part is done. Now we are left with only one last topic, that is Poynting vector and Poynting theorem. This is on power calculation. Whatever electromagnetic wave you have, or what is going to be the power of that wave. Okay, so we'll do this in the next video. Thank you.